Hi, I'm Daniel Book. I'm a mechanical engineering student here at UofL, and I'm currently in the master's program. This semester I was asked to be in charge of a capstone group while I worked on a research project at the same time, so I decided to jump on it. And so I worked with these guys over here, and we decided that we wanted to aim to try to create a custom material used for 3D printing, try to create custom filaments used for FDM printing. And we wanted to aim for the biomedical industry. So the material we ended up choosing was a PLA plastic, and we decided that because it's a common plastic used in biomedical devices such as tissue scaffolds or sutures. And one thing we wanted to look at with this project was material properties. We knew that PLA plastic it's pretty brittle. You can't really move it very much without it breaking. So we knew that another material you could add to it, polyethylene glycol, we could add that to it and make it more flexible. So we wanted to see how the different material properties would change as we added polyethylene glycol to it. And one of the other opportunities we had was a bioengineering student here at UofL was working on his thesis, trying to make a biodegradable suture out of PLA. And he heard of us trying to use 3D printing, and he heard about our custom materials we're going to make. And so he was interested, and he contacted us and asked if we would help him with this thesis and print some of his designs out for him. So that's pretty much what we did with the project. We made some custom filaments with our blends of material. We printed it out, tested it, see how the material properties changed, and we took a design from the bioengineering student. We and took it and see how we could change it to get it to work with a 3D printer. We burned some samples out. We made a lot of progress on this project so far, but there's still a lot more stuff that can be looked at, a lot more material properties that we didn't even consider. And with that being said, I'll turn it over to the capstone team, and they'll give their presentation for you.
Morning. Take good volume. I'm Jeff. Jeff Sparks, Logan, McDonald, Knaster. Like Dan said, we worked on a replacement for sutures.
Might need to 3D print that one next.
So we used 2 different molecular weights of PLA and 3 different molecular weights of PEG to come up with different combinations of the 2 material to see which ones would work the best. It basically will go in the end of the trocar during a laparoscopic surgery, and when the trocar is removed, the suture will lock into place and close the opening. Reasons that this is more beneficial than traditional suturing techniques. It reduces the risk of hernia. I'm not sure what the number is or what it will be, but it'll reduce the risk of hernia. It reduces the time under anesthesia, which is very important. The less time under the knife, the less time that the doctor has to spend on a patient. Everything just gets better from there. Okay. Next slide.
All right, so I guess I'm going to talk about our design process here a little bit. As you can see, this is our beta prototype up on the screen right here. And we went through kind of interesting design process. When we first started out, we were using a 2-piece design for this suture where this leg and then that leg were 2 pieces that would be snapped together after printing. And when we moved into this beta prototype stage, we went to one piece that utilizes this support structure that's removed after printing is completed. One of the other issues we had run into with our alpha prototype was we lacked some of the physical strength and properties we desired. So we changed the geometry of the design a little bit to achieve what we were after. One of the other problems we had run into with our alpha prototype was there was too much pressure required to insert the suture through the muscle tissue. So we found out we could offset these legs to where they don't all hit at the same time, and it reduces the amount of pressure needed to insert the suture, as well as we were able to make the points a little bit sharper. And all this was accomplished with 3D printing. Bump me over to the next slide. Here you can see where this is the printing of the suture. You can see the first picture there on the left is laying down the support structure, and then there's the completed suture on the right. The next slide. Yeah. So if you see the picture on the left here, this was the design the biomedical engineer medical student we were working with. That's the design he came up with. It utilized the two-piece design, and he put those waves in there to try and reduce the stress carried, and it worked okay. Some alternative applications that this PLA, PEG could be used for is any sort of deep medical procedure that requires some sort of support structure after the procedure, and you want that support structure to degrade over time so you don't have to go inside the body again to remove it. And then some alternative designs that were considered for the suture. We tried the two-piece design and just never really had a whole lot of luck with it. We kind of got away from that one. You don't want two separate pieces floating around in the body. If they became separated, you would run into some trouble down the road. So I'm going to pass it over to Logan here.
The suture itself is important, but one of the major aspects of this project was the material itself. In the top right corner of this graph here, we're showing the tensile strength over top of the mean modulus. Our base PLA are the blue dots there in the top right. And as we add different grades of PEG to our PLA, we can begin to see a pattern. And it's fairly linear, so we can begin to predict the type of material properties that we're going to see once we add our PEG to our PLA. Our next steps, obviously, is going to be working with medical professionals, leading to human trials. Funding for testing is definitely a must. This stuff can become very expensive. As said before, we're going to try to reduce the risk within endoscopic surgery. With the new tool in the medical field, it's quite a few endless possibilities with this type of materials. And then the FDA stated that 3 million trocars were used in 1994, 4.8 million in 2000, and 6.2 million trocars were used in 2004. So we can see a fairly steady increase. And I think that's about it. You guys got anything else? Overall, I think the material definitely shows a lot of promising aspects. Anything from skin scaffolding to bone support structures. But other than that, pretty good. Anybody have any questions?